All right, so this is the first video and the last block of videos that we're going to be doing. So let's just dive right in. So here I have the graph of the function f of x equals x squared. And I've noted in particular this point on the graph, 1, 1. So what we're going to be doing is we're going to be zooming in around this point 1, 1. All right, so in this picture, I have the portion of the parabola with x between 0.8 and 1.2. It's been zoomed in by a factor of 2.5. All right, so because this is the graph of the function y equals x squared, so when x is 0.8, the y coordinate is 0.8 squared, which would be 0.64. And likewise, when x is 1.2, y should be 1.2 squared, which is 1.44. Now, notice that this looks pretty close to a straight line segment. There's a slight noticeable curvature still, but it's pretty close to a straight line segment. If we pretend that it is a straight line segment, what we could do is try to compute the slope of this segment. In order to get the slope, we need 2 points. If I use the points 1, 1, and let's use the other point 1.2, 1.44. Remember that to get the slope, the formula is the change in y. So I'm going to do 1.44 minus 1 over the change in x. So I'm going to do 1.2 minus 1. And using a calculator, we can find that this would be equal to 2.2. Now, let's see what happens if I try to use 1, 1, and the left endpoint, where x was 0.8 and y was 0.64. If I use these 2 points, I'm going to get the slope would be equal to. All right, so change in y, I'm going to do 0.64 minus 1, and over the change in x, that will be 0.8 minus 1. And using a calculator, we can find this value to be 1.8. Notice that when we use different points, we get different slopes. And the reason why that happens is because we are not actually working with a straight line segment. What we do see, however, is that no matter which point we use, the slope appears to be around equal to 2. All right, I'm going to zoom in even more now. So here, this is a picture of the portion of the parabola with x being between 0.95 and up here where x is 1.05. The figure has been scaled by a factor of 12 now in order to make things more clear. And at this point, whereas the previous picture still had a slight noticeable curve to it, this one is practically straight. Now I'm going to do just as I did before, and I'm going to pretend that this is a straight line segment, and I'm going to try to compute the slope. So if I use the points 1, 1, and 1.05, 1.05 squared, so we would find the slope is, again, the change in y over the change in x. And using a calculator, you can find that this would be equal to 2.05. And if instead I use the points 1, 1 and 0.95, 0.95 squared, if you go through all the calculations, you're going to find the slope to be 1.95. And again, the reason why we get different slopes when we use different points is because we don't actually have a straight line segment. But again, we see that the slope appears to be around equal to 2. And in fact, these numbers that we got, 2.05 and 1.95, they're much closer to 2 than the values that we found before, which were 2.2 and 1.8. So as we zoom in closer and closer to the point 1, 1, what we see of the parabola is going to become more and more straight. And it appears that the slope is going to get closer and closer to 2. So it seems like if we see this process through to the end, at infinity, if you will, it seems that we would find the slope of the parabola at this point 1, 1 would be equal to 2. Now what we've done is not very rigorous, so I want to be more precise, and I also want to generalize beyond just looking at the function f of x equals x squared. All right, so here I just have some arbitrary function f of x. I have a picture of its graph. I've marked one particular point on the graph with x coordinate a and y coordinate f of a. And just as before, I'm going to zoom in near this point. And when we zoom in around this point, the portion of the graph that we see is going to look pretty close to a straight line segment. What we can then do is choose a point on this segment. It doesn't even have to be the endpoints, but you just choose a point near it. And then with these 2 points, what we can try to do is compute the slope. So if I do the change in y over the change in x, let's do f of x minus f of a for the change in y. And then over x minus a for the change in x. I suppose to be more precise, what I should do is maybe put quotes around the word slope actually, because this isn't the slope of anything just yet. Remember, this is still a curve, not a straight line segment. However, as we zoom in more and more, the curve becomes more straight, and the idea is that this quote-unquote slope will approach the slope of the curve at the particular point a f of a. One thing to notice is that as we zoom in closer and closer, our x values are going to be moving closer and closer to a. So we could say that x will approach a in the end. So if we want to ask, what would the slope be at the end of this infinite process? Well, to get what lies at the end of an infinite process, that's where the notion of a limit comes into play, right? So this is what we discussed in the very, very first video of this entire workshop series. So the slope at the end would be the limit as x approaches a of this expression here. So here I'm going to highlight to summarize what we've done. If I have a function f, we're going to define the slope of the graph of f at this point a f of a which we're going to denote with this expression here. So we read this as f prime of a. So f prime of a is representing the slope of the graph of f at this point, and it's defined to be the limit as x approaches a of this expression, f of x minus f of a over x minus a. We've seen that it's possible that a limit won't exist. Therefore, I need to specify provided the limit exists. If the limit does not exist, then the slope of the graph at this point would remain undefined. Now, if we replace x with the expression a plus h, then in the numerator, instead of f of x, we would have f of a plus h, and then minus f of a over. And in the denominator, again, if we replace x with a plus h, the a's would actually cancel out, and you would just have h in the denominator. And then if x is equal to a plus h, then to say that x is approaching a, h would have to be approaching 0. So instead of writing the limit as x approaches a, we could write it as the limit as h approaches 0. And this gives us an alternative definition for f prime of a. It's an alternative, also equivalent definition. So you'll actually probably see both formulas when you're studying calculus class. And then this function, f prime of x, that we get from this formula is what we call the derivative of f. So if you remember, I talked about how you would be studying limits, derivatives, and integrals. So this is the second object that you're going to learn about in calculus, the derivative. We're pretty much going to wrap up our video series with the derivative. We're not going to study it in depth, we're just going to introduce it, okay? So I'm going to end this video at this point. In the next video, I'll work through just a few examples of computing derivatives. In theory, by now you guys have some experience in evaluating limits, so it should be a fairly simple video, all right? Okay, thanks for watching.